Hello and welcome. I am Engineer Steinberg, joined by Engineer Wang. We are the heads of the Pan-Pacific Defense Corps Engineering Division. Today we will be discussing Jaeger Balance Control. We were tasked with creating the Jaeger Balance Controller after a number of Jaegers were untimely destroyed in preventable losses. Let us explain how the balance controller works. The vertical base is in frame 0. There's no movement here. Arm 1 rotates about the Z1 axis in frame 1. This arm is always parallel to the ground. Arm 1 moves in a positive direction when it is rotating counterclockwise. Arm 2 is at the end of Arm 1, rotating about the Z2 axis in frame 2. Arm 2 moves in a positive direction when it is rotating clockwise. This is important to keep in mind when the Jaeger is out in the field.
After creating a model of the robot in a simulation, we needed to add the physics of it in. We did this by using Lagrangian dynamics. The Lagrangian takes the total kinetic energy of the system and subtracts it from the total potential energy of the system. Using this, we can solve for the dynamics of the robot. Rearranging the equation in MATLAB, we are able to create a function that takes in the position and the velocities of the two links and the voltage of the motor and outputs the new velocities and acceleration of the Jaeger. By taking the derivative of the output, we were able to get the new positions and velocities of the links and plot the movements in our simulation, thus completing the physics engine of the Jaeger. At this point, the physical parameters used in the dynamics equations were estimations based off of previous Jaeger prototypes. Although the values used so far make the simulation look realistic, better values can be calculated to match the physical parameters of our actual robot. This can be calculated through the use of Hamiltonian mechanics. The Hamiltonian of the robot is the sum of the total kinetic and potential energies in the system. This can be rewritten in the form that the total amount of energy put into the system is equal to the energy that is physically observable and the energy lost. The equation created to describe this can be seen on the slide. In the equation, there are 6 unknowns, which are all of the thetas. To accurately solve for the 6 unknowns, we record the position and the velocity of the robot at 10,000 different time points, thus creating a system of 10,000 equations to solve for 6 unknowns. However, for the 10,000 equations to produce an accurate output of the unknowns, they had to represent as many unique positions of the robot as possible. To achieve this, we buzzed together 2 sine waves and inputted as the voltage to create a sporadic movements for the robot, hoping for as many unique configurations as possible. This process was done for the simulation and again for the actual physical system. The results of these can be seen here for the simulated theta values and here for the actual theta values. Plugging the actual theta values back into the dynamics of the Jaeger, a more accurate physics engine is created.
This is the entire balance control system of the Jaeger. The system is made up of several integral components that improve the Jaeger's fighting ability.
The subsystem highlighted here in the slide is the servo portion of the robot. The servo portion of this program takes the place of the dynamics function, which takes in the voltage from the controllers and the outputs of the position and velocities of the 2 links. The gains are used to match the parameterizations used at the beginning.
Here is the multi-port control switch. Using the state decider, the switch activates different control functions based on the Jaeger's state position. The state decider function selects a state for the system, and then the switch activates a control function using the Jaeger's state position. The switch will either activate the swing up function, a do-nothing state, or the balance function, or the 4th state. This is a critical feature of the system. Without the control switch, the Jaeger will be unable to effectively fight against the dreaded kaiju. Given the Jaeger's position, it can occupy 3 different states. If the robot has fallen and is within 10 degrees of the ground, the robot is in Zone 1. If the robot is within 20 degrees of its standing position, it is in Zone 3. If the robot is outside of those ranges, it is in Zone 2. Zone 1 activates the swing-up function. Zone 2 does nothing. Zone 3 activates the balance function. The state decider function takes the zone that the Jaeger is in, compares it with the Jaeger's position, and decides what state to move the Jaeger to. The Jaeger can only move from state 1 to state 3, from state 3 to state 2, from state 2 to state 1. However, if the Jaeger falls in an unnatural position, it is placed in the fourth state. The fourth state moves the Jaeger back to a normal position, puts the Jaeger back into state 1, and then the swing up function is activated. Another way to implement the fourth state would have been to activate the swing up function from the Jaeger's down position. When the Jaeger is in state 1, the swing up function is activated. The swing up function is made up of a closed loop. The function takes in the Jaeger's positions and velocities in Q1, Q1 dot, Q2, and Q2 dot. The desired position is subtracted from the actual position, and they are fed through the Kp and Kv gain values. These were found by using the Jaeger standard percent overshoot and peak times of 5% and 0.15 seconds. This is one of the most important parts of the Jaeger's balance control system. Without a working swing up function, the Jaeger will be unable to get up in the middle of a fight and will be downed, leaving it exposed to any enemies.
When the Jaeger is standing upright and is not leaning more than 20 degrees forward or backwards, it enters the third state and uses a balance control to keep the robot balanced. The most balanced conditions for the Jaeger is when the velocity of the first link, Q1 dot, the position of the second link, Q2, and the velocity of the second link, Q2 dot, are all 0. In theory, the position of the first link, Q1, should not matter for the most balanced conditions. However, for convenience, we have also set it at 0. This is the desired positions and velocities. By taking in the actual positions and velocities, the error can be found. To get the robot to balance again, the controller must push this error back to 0.
The engineering team developed a feedback loop to control the position of the Jaeger. This feedback loop takes the difference between the desired position and the actual position and feeds that back into the Jaeger's control system. We have implemented 3 separate position controllers. The first controller allows us to move to an exact spot. A Jaeger pilot is able to input an exact position into the feedback loop and move the Jaeger to that position. Arm 1 of the system will move to the desired position. This is ideal for security missions. The second controller allows the Jaeger to follow a time-based position signal. The Jaeger pilot will apply a time-based position signal to the Jaeger. The Jaeger will oscillate back and forth between a given position. This is ideal for patrol missions. Our last position controller allows the Jaeger pilot to use an analog controller. This is a safety precaution should any circuits short out within the Jaeger cockpit. Jaeger pilots will never lose control of their Jaegers, no matter what circumstance. The position controller is not necessarily needed. However, it is an important part of the Jaeger's balance control system. This was the last system that the engineering team implemented, and it gives the Jaeger pilots the freedom to control their own Jaeger. Thank you for tuning in and learning about the Jaeger's balance controller. Hold on, we're getting word of an incoming kaiju attack. There's no way. They found the lab. How are they attacking here in St. Louis? Red alert, all hands to battle stations. Suit up the Jaeger. Oh no, the circuits were fried. Switch to analog control. Thank you for joining us. You've seen the Jaeger in action and how the balance controller helps the Jaeger during the fight. If you have any questions, feel free to contact the Pan Pacific Defense Corps Engineering Division. Thank you very much and have a nice day.